I think.
Thanks, Daniel.
Yeah, you're frozen.
Thanks, Daniel. Can you hear me?
Yeah, I can hear you.
Oh, frozen.
A little bit, yeah.
Okay.
Yeah.
Now I'm live again.
Yes, you're live again. Yeah.
Okay. As usual, thanks the organizers, Daniel, Gillian, Valentina, for the invitation. Very happy to see each other on the screen, and also very happy to talk about some mathematics. Okay, so my talk is actually have 4 parts. So in part 1, I'm going to give an introduction about the equation and the problem we are going to look at. And second part is the recent global regularity in optimal transport, which is a joint work with Shibing Chen and Xu Jiawang. And third part, I'm going to talk about some application of optimal transport. We're actually trying to use optimal transport to understand how the universe is going to evolve. So this is the joint work with Gregoire Loper. And the last part depends on the time. If we do have enough time, I can give you some very brief idea about the proof. Okay. All right. Now let's starting from the part 1. So the equation we are going to look at is a standard Monge pair. So that's a determinant d2u is equals f. However, the boundary condition we are going to look at, which is the natural boundary condition, du omega is equals omega star. Okay. And in this talk, we are going to assume the function f is given and which is positive function. So therefore, we look at the convex solutions, and the equation will become elliptic equation. Okay. The domain omega star, we assuming they are bounded, and the convex domain with C11 boundaries. Okay. This boundary problem is actually has many interesting applications, especially in optimal transport and the minimal Lagrangian and the convex geometry as well. Okay. Now we're starting from the optimal transport. Use a pen. So optimal transport is actually we have initial domain omega, and we have some material which the distribution is given by a density function rho, and we have a target omega star, where we have the density function rho star, and we are trying to do the mapping from omega to omega star by a mapping T. So under such a transport mapping, we have the total cost, which is given by the functional. So this is the functional under the mapping T. And while the C is actually the cost function. I'm not sure if anyone already seen this before, but however, we're trying to minimize such a total cost, and the minimizer is called optimal mapping. And of course, we're assuming all the mapping is measure preserving. So that means when you do the transport, nothing extra is gained and nothing is lost. Okay, so the measure is preserved. Okay, in a very standard situation and a very classical situation, we assuming the cost function cxy is a quadratic cost function. So that means how much it costs you if you want to transport from x to y is given by exactly x minus y, the Euclidean distance square. Okay. So in this classical case, we already know the optimal mapping T is actually given by a gradient of some function u, which is the potential function. And moreover, this potential function is a convex function, and it satisfies exactly the Monge pair equation and subject to the natural boundary condition, because the mapping T is given by du. So we are trying to map everything from omega to omega star. So that's the reason why the boundary condition is du omega equals omega star in the classical case. Okay. Another application for this boundary value problem is coming from the geometry. So let's look at it in dimension 2. We're assuming we have 2 domains, smooth domain with equal area, omega and omega star. And what we're going to look for is we looking for some diffeomorphism f from omega to omega star. Without any other restriction, we know there will be infinitely many diffeomorphism mapping from omega to omega star in general. But however, we are looking for this diffeomorphism to satisfy the 2 conditions. So the first condition is area preserving. And second condition, we are looking at the graph of such diffeomorphism f. So the graph will be a 2-dimensional submanifold embedded in R4, right? Because omega and omega star is R2, is 2-dimensional domain. So therefore, the graph of the mapping f will be a 2-dimensional submanifold in R4, and we require such a mapping, such a graph to be minimal. Okay. To say this mapping F is area preserving, which means the graph will be a Lagrangian surface in R4. And to say this graph is minimal, which means the Lagrangian angle will be a constant. And we can choose a proper coordinate such that that angle, I don't remember it's 0 or pi over 2, but we have a special angle such that this mapping F is exactly equal to the gradient of some function u. So F is equal to du. And this function u, again, is satisfied our Monge pair equation. That's a determinant d2u equals 1 because because the area is preserving and both one has an equal area. And the boundary condition, again, is a du omega to omega star. So that's exactly the diffeomorphism F we are looking for. Okay, so that's two interesting applications. Okay, now is some kind of remarks. So we follow the language of Pogorelov. The natural boundary value problem is also called second boundary value problem. The first one is referred to the standard Euclid problem. And in 1950s, Pogorelov assuming as far as the domain omega and the omega stars convex, and then he proved there exists a generalized solution, the weak solution, which is in the sense of Alexandrov. And in 1990s, Brenier is actually proved another kind of sort of different weak solutions. And he only assuming the boundary is zero measure. So zero measure means n-dimensional Hausdorff measure is equal to 0. And also he needs some kind of balance condition. So that means the integration of the F is equal to the volume of the target domain, omega star. So in this kind of, under such a assumption, Brenier proved there exists a unique weak solution, but that is a little bit weaker than Alexandrov weak solution. Okay. But we are not talking about the weak solutions. Our study is going to fix on the regularity theory. So especially we are looking for the global regularity of the solution satisfied such boundary value problems. Okay, so that's our goal. Okay, now in dimension 2, if both domain omega star are uniformly convex, and then Delanoy in 1991 is proved the solution will be globally smooth as far as the right-hand side part of the PDE is smooth enough. Okay, and this result was extended by John Roberts in 1997, and his result cover arbitrary dimension. So again, they need to assume in the domain uniformly convex. And in 1996, Caffarelli is actually reduced the assumption a little bit, and he proved as far as the domain, and again, he need the domain to be uniformly convex, but however, the boundary regularity only need to be C2, and the right-hand side part of the PDE is C alpha, then Caffarelli proved the solution is C2 alpha prime globally for some alpha prime less than alpha. Okay, as you can see, both the above result need to assume the domain is uniformly convex. So in the smooth case, the uniformly convex corresponding to the curvature is strictly positive. Okay, if the curvature is negative somewhere, then we have the counterexamples to say the solution may not be C1. So that means we cannot expect too much regularity when the curvature is negative. So therefore, the critical case, if the curvature equals 0 somewhere, so that's a degenerate case, and also the critical case become more interesting. So recently, joint work with Shibing Chen and Xijia Wang, we actually obtained the regularity in the critical case and also the degenerate case. We only assuming the domain omega star to be convex. So that means the curvature could degenerate to be 0. Okay, it may have a little bit flat part. And the regularity for the boundary only need to be C11. Then we prove as far as the right-hand side part is C alpha, the solution will be C2 alpha globally for the same alpha. So that's our recent result on the global regularity. And But however, all this result, the global regularity is corresponding to the standard Monge pair, which again corresponding to the cost function. Cxy is a quadratic cost function. So that's a half x minus y squared. So that corresponding to the very special case of the cost function. And for the general cost function, what can we do? For the general cost function, it's actually, we know that the potential function u is satisfied. Again, it's a Monge pair type equation, but you have a matrix on the left-hand side part. It depends on the cost function. And the natural boundary condition, again, is the T omega equals omega star, because we transport everything from omega to omega star, whereas the optimal mapping T not only depend on the gradient of u, it also depends on the cost function, of course, okay? So what's the regularity for that one? A major breakthrough was given by Shinama, Liu, and Xujia in 2005, and they discovered a necessary and sufficient condition, which is now called MTW condition. So the condition is inequality here. That's pretty long, you can see, because it involves the first order derivative of the cost function. So, but however, in geometry, we have a much better understanding for this inequality. It's related to the section curvature, but it's not totally equivalent, but it's related somehow, okay? And I'm not going to talk about too much about this condition, but as far as the cost function satisfied MTW condition, then Ma Challenger 1 and also Challenger 1, they can obtain the global regularity as well by assuming the domain satisfies some kind of uniformly C convexity. Okay, so that's the story for general cost function. And moreover, the above condition for cost function and for the domain is actually sharp, because Gregoire-Loper, he proved if the MTW is not satisfied, then the C1 regularity will fail, okay? So if U is not C1, that means the optimal mapping will not be continuous, because optimal mapping is actually dependent on DU, okay? And so that means the MTW condition is actually sharp, it's necessary and sufficient. And for the convexity of the target, in Martin 1 and also Caffarelli in the standard case, they show there is counterexample, which means if the target is not C-convex, or in the standard case, if the target is not convex, then the C1 regularity will fail again. So that means the optimal mapping, again, is not continuous. Okay, so that's pretty much to say this result, this theory is the best one we can expect it. Okay, so that's the story for standard optimal transport. And what we are going to do with Gregoire-Loper is we try to use optimal transport to understand how our universe is actually evolving. Okay, so we consider the following model. We assuming we have some kind of distribution with the matter with density rho. So you can imagine it's a density of the stars in the sky, okay, the planet, the stars, and they are moving along a velocity field, which is given by V, that is a vector field. And moreover, during the evolution, all the stars is actually accelerated by some kind of gravitational field, which is given by a potential function P. And the P is actually depend on the matter. It depends on the distribution of the star. So it depends on the rho. By using the PDE system, we actually have three equations. So the first one tells us the conservation with the mass. So that means original how many stars long time ago and how many stars, I mean, the total mass is still preserved, okay? And second one is tells us the star is actually moving according to the acceleration field, okay? And the third equation is a Laplacian P, that's a boson equation. It actually tells us how the gravitational field is generated by the matter rho. Okay, as you can see, these three equations, they actually tangle with each other, right? So that makes the problem pretty hard. So the reconstruction problem is actually assuming we know the distribution when time equals 0. So that's the initial time. Assuming we know the distribution at the initial time, and we also know the distribution at the terminal time when time equals capital T, then how can we understand the distribution in the middle. Okay, so in a different way, as far as we know the initial distribution of the universe, and we know the universe today, and how can we recover the universe maybe 1 million years ago? Okay, somewhere in the middle. Okay, so that's a reconstruction problem, satisfy such a boundary condition. And of course, you can consider another different kind of boundary problem, which is a Cauchy problem or initial value problem. So initial value problem, that means as far as we know the distribution at the initial time and the velocity at the initial time, then how the universe is evolving. But somehow, if you think about the Big Bang theory, the Big Bang theory tells us the universe is actually coming from a singularity point. So at that point, we know the distribution, but however, it's pretty hard to know the velocity, because velocity is actually like a bombing, right? So the velocity is actually will be singular. So that makes more sense. We talk about a reconstruction problem. So that means initial is a Dirac measure, and today we know, assuming we know the distribution of the universe, and then we can understand how what happens in the past time. Okay. Actually, Gregoire himself in 2006, he actually formulated the above reconstruction problem as a minimization problem. So the problem is corresponding to minimize the following functional, which is the action. As you can see, it has two parts. So the part one is actually the kinetic. Is that called kinetic? That's a kinetic energy. And second part is the potential energy. Okay, it's given by the gravitativity. Okay, so that's the functional we're trying to minimize. If we minimize this functional, the Euler equation will give us exactly the second equation in the system. Okay, so we minimize this functional and of course overall rho v and p, which satisfy the equation 1. So that's the measure preserving, and the equation 3, that's the Poisson equation as well. But in Gregoire's paper, he only considered the torus case. So it's not a global, because he don't want to discuss about the boundary conditions. So he assuming the universe is actually periodic. Okay. Recently, in our joint work, we actually consider a little bit more general situation. Instead of considering the potential energy is given by the gradient of p square, we actually consider it's given by some kind of internal energy, the curve f. Okay, so that means we replace this quadratic term by a more general function f. And so therefore, the energy we are going to minimize is the following. Okay. This problem is, in the past, it was also studied by Paul Lee and Robert McCann in 2011. So what they consider is they consider the energy is given by the integration of the density rho multiply a function q. So the physical meaning of the function q is actually tells us when the matter is evolving, it has an external acceleration field, which is given by the gradient. So that's a power force coming from the exterior area. It's given by the gradient of the function q. But however, it's not interacting. So that means each star, they are not talking to each other. Okay, they are just moving by themselves. There's no interacting. So different star, they have the different parts. There's no interacting. Okay, and it's evolving according to an external acceleration, which is given by the gradient of the q. Okay, so in that case, Paul Lee and Robert McCann, they actually able to formulate this problem into optimal transport, where the cost function is actually given by cxy. So in their proof, in their result, the cost function is given by cxy, which is actually, let me draw a picture. Imagine you are moving from a position x to position y. You actually have to pass a curve. The path is called gamma. Okay, so the gamma is actually a smooth curve connecting x and y. then the cost function is actually given by the gamma dot. So that's a derivative of the gamma half square, and plus this external function q. That makes sense? Then we are going to choose the minimum. So of course you have the different paths from x to y, right? Then we choose the infimum. So the infimum is actually the cost from x to y. That's a cxy. Okay, so Pauli and McCann, they can formulate the above reconstruction problem into optimal transport with this specific cost function. Okay, and moreover, when they assuming the external function q is given by epsilon multiply a function v for a very small epsilon, for epsilon small enough, and the v satisfies some kind of structure condition. And again, it's pretty long, some kind of inequality. Then they prove the above cost function actually satisfies the MTW condition. If the cost function satisfies MTW condition, then by using the theory of optimal transport, we can say the optimal mapping is actually smooth, as far as all the other data are smooth. So optimal mapping is smooth, then we know the universe is actually evolving along a smooth behavior. Okay, so because each star, the path is actually a smooth path. Okay, so that's in the special case. And what we are doing with Gregoire is actually we consider a different situation. We're assuming this force, this external force, we don't know where it comes from. Okay, we're assuming this force, it only acts, it only happens, it only occurs in the middle time. So that means the Q is only when the time in the middle, in the half T, and it occurs. So that means the universe is actually evolving by himself, but suddenly something happens. Okay, everything is changed by some kind of external force. Then after it happens once, then it moves again. Okay, so in that situation, the function that we are going to minimize is actually also change a little bit. So the kinetic, so what I mean is kinetic. The kinetic energy doesn't change, but the potential will be the second term will change to the following form. So which means it only happens when the time equals half of the t. Okay, so under such a restriction, we can remove the smoothness condition on the Q, because before the McCann and the Pauli and the Robert McCann, they assuming the Q is actually epsilon multiply V for epsilon very, very small. But now we can remove the smallness condition. And moreover, so what's the motivation we are considering this is actually, let's imagine you have some kind of evolution from X to Y. Now, if it only happens somewhere in the middle, we actually have two segments. And now our motivation is actually, as far as you can handle the middle time situation, then you can consider more approximations. So that means when the n is going to infinity, our motivation is actually to use a discrete case to approximate the smooth case. Does that make sense? So that's actually our original motivation. Okay. All right, so what's our result? So by considering this two-step evolution, we actually can understand everything very clearly. So what does that mean? That means we can prove there exists at least one admissible solution. So admissible solution, I mean, that's kind of the weak solution that makes sense. Okay, such that it satisfied the mass balance condition, is satisfied the evolution condition and the Poisson equation in the weak sense. But we are not going to give much definition for the admissible solution. But anyhow, more than that, we can understand the initial velocity is given by a potential function phi. Okay, so that initially we can calculate the velocity, the vector field, and moreover, the optimal velocity is given by the following. When the time is from zero, sorry, that's the title, from 0 to half t. So when the time is from 0 to half t, each star is actually moving along a constant velocity. and up to this is time half t, this is time 0, this is time t, okay? So it's moving along a constant velocity. And moreover, the density, the distribution when the time equals half capital T is given by the push forward of the original density functions. And after the time passes the half capital T, then the star is going to move along a different kind of velocity, okay? So what happens here is exactly being affected by external force, the power force Q, okay? So we can describe very, very clearly what's the velocity, and moreover, we can describe what's the optimal path. So that means we can write down the path of each particle, okay, by giving by this formula, okay.
Jiakun, just one question.
Yeah.
So you are using then at the end as well optimal transport, but you did not say which cost function you are using. So you introduced the new integral, but you did not write that what is actually your cost function at the end.
Yeah, I haven't. Yeah. I mean, you are much faster than my presentation. I haven't been there. Yeah. So currently.
Excuse me for interrupting. Okay.
Yeah. Sorry. I mean, currently we haven't used optimal transport. Okay. So in this part, we haven't. Yeah, we haven't formulated it into the optimal transport. But in the next slide. Okay. Now we come to Daniel's question. So what's the reason why we are going to use optimal transport, the formulation of optimal transport, because we try to study the regularity. If you go back to the PDE system, where it is, this system, the regularity is actually not well understood. Okay, so people can talk about a weak solution, but however, when you move to the classical smooth regularity, very little result is known. Okay, so that's the reason why we are thinking to use a different way to study this PDE system by using optimal transport. So Paul Lee and Robert McCann, they did step 1. They consider special situation and they have the cost function. And under a special condition on this cost function, such that it satisfies MTW, then they have regularity, okay? But now we are going to consider a different model. And again, we're trying to formulate our model into the optimal transport. And how we do that, we have to do some kind of modification of the functions. So by modify the function phi, so the phi is a potential of the velocity field, okay? And also we modify the function q. So the q is external force field, okay? By doing such a modification, and by the observation, this mapping M is actually push forward the initial density rho 0 to the terminal density rho t, okay? Then very naturally, we have a Monge-Ampere equation. So the Monge-Ampere equation comes, so that gives us some kind of hope. It's related to optimal transport as well. Then how can we discover the cost functions? So that addresses the question of Daniel. So we can prove the above problem is also related to optimal transport, where the cost function is given by the Q star. So the Q star is the Lambda transform of the Q. Sorry, I mean, talk about the theta. We have to modify it a little bit, okay? So the cost function is actually given by the external force, the Lambda transform of the external force, okay? And similarly, we can assume the external force, the Q, satisfied some kind of structure condition, which is very similar to MTW. Okay, so under that kind of assumption, the cost function will satisfy MTW in optimal transport. And from MTW condition, we can obtain a lot of regularity from the theory of optimal transport, such that as far as the density is LP, for P large enough, the velocity potential function will be C1 alpha. And if the density is smooth enough, then the velocity again is smooth enough. If the velocity is smooth, then we can control all the paths of the particles. Sorry, I think the time is very short. Okay, so before I finish, I want to talk about a little bit more about the Midfield case. So the Midfield case, before each star is actually moving independently. Okay, they are not talking to each other. The star is actually not interacting with each other. But the real case generated by the gravitational, the star is actually attract each other or repel each other. It depends on different kind of stars. Okay, so in that situation, what's the force? What's the force field? The force field is actually given by some kind of kernel. The kernel is it's kappa here. So the external force is actually given by the density and the kappa. The kappa is the kernel. So in the standard case, that's exactly the Coulomb kernel, okay, corresponding to the Laplacian equation. Okay, so in that case, the functional we actually going to minimize is again had two parts. The first part is a kinetic, and the second part is a gravitational, gravitativity. Okay, so second part is the energy coming from the gravitativity. Okay, as you can see, it's kind of convolution. It's a convolution happens there. I mean, it makes sense because it's coming from the Laplacian equation. Okay, so in that case, we have to assuming a little bit stronger condition for the kernel. We're assuming the kernel satisfies the first order condition, which is very similar to MTW. But if you look at MTW more carefully, you can see this is stronger because we don't need to assuming the theta perpendicular to eta. Okay, there's no such a restriction. So that means MTW is satisfied along all the directions, along all the epsilon and along all the vector direction. It doesn't to be perpendicular to each other. So under such an assumption, we can prove our cost function also satisfied MTW, and then from there we have the regularity. Okay, maybe just half minutes. So what's the reason why we assuming the stronger one? Because the MTW condition is actually not preserved under the convex combination. Okay, but however, MTW without orthogonal, we can prove it's actually preserved. It's preserved under the convex combination. So therefore, it's preserved by the convolution. So that makes sense when we study the Laplacian equation. Okay, okay. So yeah, after that, that's a proof. So we can skip about the detail of the proof. I think that's all I would like to talk today. Where's the thank you? Gosh.
It's okay.
I'm going to thank you for all of you.
Thank you, Jiakun.
For
this very interesting talk.
Yeah, it comes. Thank you.
Thank you, Jiakun. And it's a very nice application, and you use so that you are using basically optimal transport to derive stronger regularity conditions of a variational problem where you already have actually solutions, but to derive better regularity, you use optimal transport methods. I think this is a very nice idea. Any questions or remarks by the audience, please? No, I like Matt's cat.
He really wants to be involved.
I see. Yeah, fair enough. Okay, if nobody has any question, we are going now in the lunch break. I would stop now the recording and also this meeting, basically. I think many people have Christmas parties. We will have Pure Maths meeting with University of Sydney. So everybody's busy, and we will resume at 2:30. And this time, please use the other Zoom meeting because the recording happens at Wollongong with a strong internet connection, of course. But no, it will be from Glenn's computer, so it is at home actually. So it
that's right. Fiber to the premise. Fiber to the premise.
Yes. Okay. Thank you so much, everybody, and. For the morning session. Thanks to all the speakers of the morning session, of course, please. So thank you, Adam, Hong, Noah, and Jiakun again. And we are looking forward to the afternoon session. Okay.
Thank you, Daniel. See you all then.
Bye. Hi, G. How are you doing? Hi, Florica. Chipach.
Hi. Sorry to be late. busy
No,
in
it's
the
okay.
morning.
Don't worry. Everything is okay.
Just catch up Jiakun's talk.
Yes. It's a very nice talk. I mean, I like that you use optimal transport methods to derive regularity of a variational problem. Yeah. Florica, how are you doing? Oh, she's away. Okay. Okay, I see you in the afternoon session. I also have pure maths meeting. Sorry. See you.
Sure,
Bye.
Sure. See you.